We now take a look at the Simple Network Management Protocol, or SNMP, that supports communication of network management information within the IP network. Management framework solutions for TCP/IP networks were introduced as hardware and software increased in order to support rapid network growth. SNMP was originally adapted from a more simpler SGMP protocol for use as the basis for common network management throughout the system. SNMP has since experienced version revisions, however remains the standard protocol for network management. The SNMP framework, as well as the supporting management information base, act as the foundation for network management, and are introduced in support of a well-rounded understanding of the network management framework for TCP/IP. So upon completion of this section, it is generally expected that trainees will be able to describe the SNMP architecture and messaging behavior, describe the function of the management information base, or MIB, and configure general SNMP parameters and traps. SNMP is primarily used to support the communication of network resource information of network elements, such as devices that report to a network management station, or NMS. We can consider, for example, elements such as those shown in this example, in the form of routers and switches, each containing a number of components and performing a number of operations. The status of such resources is obtained and communicated by SNMP and delivered to an NMS to enable effective network management in near real time. Furthermore, SNMP is designed to support trap messages that report certain network issues and failures quickly to ensure network downtime is greatly minimized. It may also be used to manage applications, accounts of users, licenses for products, and various other equipment such as workstations and servers. As the enterprise network grows and covers a larger geographical distance, it may become ever more difficult to manage the network and its components. However, through SNMP, networks can be managed centrally to provide better response times to network issues and also detect potential problems before they arise. We can understand network elements to be devices such as host terminals, gateways, and switches, for example, which will contain two components that are used to support network management features. These are referred to as the management agent and a management information base. The management agent is found within the network element in order to perform network management functions based on requests received from the network management station. The management agent will then be responsible for retrieving and altering variables found within the management information base. The management information base, or MIB, is the other component that is used to store variables regarding the state of an element. We can think of this as an information library that is used to record a whole range of information regarding the network element, from the system temperature and fan speed to the amount of data that is carried over an interface and whether the interface is even operational. For each of these variables, they are referred to as MIB objects, and it is these objects that are used by SNMP to report through SNMP messages the state of a specific MIB object. The management information base is structured in the form of an inverted tree in order to maintain a clear order to the managed objects and collected variables. At the base of the MIB, we have the root, from which three top-level objects can be found, named CCITT, that refers to the ITU-T standards body, ISO, and the joint branch of both organizations. The example shows the typical branch that is used, which contains the internetwork-specific objects referring to system and interface variables, for example. These branches are referenced using the object identifier values, or OIDs, that reference the path based on the number which we see associated with each level. The path to the IP branch, for example, would be referenced as 1.3.6.1.2.1.4. The branch in which these objects belong is now referred to as the MIB2, that is basically an update to the original management information base. Communication within SNMP is supported through the use of 5 different SNMP packets, or protocol data units, that are exchanged between the SNMP management process of the NMS and the SNMP agent process within the network element. The example we see here demonstrates the communication flow involved for each of the SNMP PDU. We start with the GET request that informs the agent that one or more parameter values are to be read from the MIB. The GetNext request informs the management process that it wishes to read parameter values in an alphanumeric order from the MIB of the network element. The SET request will be used to make changes to one or more parameters in the MIB of the network element. In response to requests made, the GetResponse PDU is used to supply the NMS with one or more parameter values. Finally, we have the trap that is generated should some important or critical event occur, of which the NMS must be urgently notified. We see in the case of most PDU, they are transmitted via UDP port 161, with the exception to the trap that is delivered to UDP port 162 of the receiving NMS. The process of protocol evolution resulted in a number of revisions to the SNMP protocol, from which the SNMP version 2C was created. From this version change, we find updates to both the protocol and also the management information base were performed. This included the addition of the get bulk request PDU to allow information from multiple objects to be requested in a single request, along with the inform request PDU that supported NMS to NMS communication of MIB information as a means, for example, of sharing information regarding the occurrence of a trap to which acknowledgements are to be received in response to such notification. The changes to the MIBs resulted in the MIB2 being created that saw a range of new objects being included within the MIB. Another update was the counter found within certain MIB objects. We see an example of such typical objects that exist in the MIB, and in particular we focus here on the example using the counter, which originally was based on a 32-bit value. However, with the increase in interface speeds, values were able to wrap after cycling through the entire bit range. Since the information is polled every 1 to 5 minutes, it may be unclear as to what the true bit value is, particularly when this counter cycles more than once. This was fixed by implementing a 64-bit counter that prevented the likelihood of wrapping from occurring. SNMP was further updated with the introduction of SNMP version 3, in order primarily to apply security features to the protocol. It is possible that requests by an NMS be subjected to what is known as man-in-the-middle attacks, in which returned MIB object information is intercepted and altered before being forwarded to the NMS in order to provide false readings regarding the status of the network element. SNMP version 3 introduces data integrity in order to prevent alteration of the response messages from a network element, data origin authentication to verify the identity of the sender, confidentiality to ensure information is not disclosed to unauthorized recipients, and protection against reusing MIB object information for illicit purposes outside of a given time frame as part of what is known as a replay attack. We demonstrate here how SNMP is implemented on a network element, which in this case can be understood as RDA. We are required to initiate the agent process on the network element, and this is achieved through the SNMP agent command. We may also be required to specify the particular version of SNMP that is to be used. Within VRP, all versions of SNMP are enabled by default. However, if we wish to use only specific versions, the SNMP agent sysinfo version command can be used to select the relevant version. If the network element is to support trap notifications, the SNMP agent trap source command should be used, followed by the interface via which traps are to be forwarded in order to allow them to reach the NMS. In order to check the current configuration settings, we can use the display SNMP agent sysinfo command that will display the current supported versions of SNMP. Since it is likely that many network elements will exist, it is important to be able to distinguish between each. This is also possible through the SNMP agent sysinfo command, through which contact information and location details can be registered. In this instance, however, we have maintained the default configuration settings. So to summarize this section on SNMP, we just have a couple of questions again here. The first asks, which versions of SNMP is or are enabled by default? Well, if we recall, all versions of SNMP, which includes versions 1, 2C, and 3, are enabled by default. What is the destination port number that is used by an agent to forward traps to a network management station? Well, all traps will be sent to the NMS via UDP port 162.